we are the Multiple LED Cube Controller Group. My name is Patrick Meissen, and this is our project. It is an LED array that is 5 by 5 by 5, so we have 125 LEDs all soldered together. We're able to turn on each one of them to display a really interesting looking pattern.
Evening, ladies and gentlemen. My name is Alex DeZiegel. You can probably do a search online for one of these LED cubes, but the thing you won't find in any of those that makes ours unique is this little wireless transmitter here. What also makes them unique
is when you put them together, the computer can recognize that the cubes are connected, and then a pattern will go from one cube to the next. It'll also go back too, which is really awesome. My name is Tao Trang Huang, and I hope you enjoy the rest of the video.
In this video, we will be covering an overview, the engineering requirements for our project, the block diagram, and final advice that we'd give to next year's students. First, the overview. The multiple LED cube controller is comprised of a computer program to determine patterns to be displayed, wireless transmitters, and LED cubes with 125 RGB LEDs, which can be displayed in interesting patterns. Second, the requirements.
The first engineering requirement, it is the battery change. The customer requirement states that the system should be simple to use and maintain. The engineering requirement is that at least 9 out of 10 users can change out batteries on LED cubes in 2 minutes or less with a manual. And that manual will tell you that you need to open the cube and take the enclosure off and remove the batteries by pulling this out, and then taking the batteries out and then changing them with a new one and then putting them back in, and reverse the order of how you did it. For the second engineering requirement, that is the cube connection. The system should have a quick response time. The engineering requirement states that a pattern can utilize the connection of another LED cube within 10 seconds of connection. Connection is when 2 LED cubes are drawn together and held in place by their magnets.
Here we're going to test the cube connection, specifically the sensors. So we're just going to need one cube turned on for this, but we're going to be using the LED from this, the magnet from this, to turn the Hall effects on for this. And I think the LEDs will change to show that there's a connection.
So we need to line the magnet up, push it together,
And then within 10 seconds, as you see, it'll pop across, and then it'll pop back to show that it's no longer connected.
do this for all 4 sides, line the LED up, push the cubes together,
Changes back.
Magnet and Hall effect, push it together,
Saw each other, back to normal.
and I think this is the 4th side. LED and magnet,
Or a Hall effect sensor and magnet, they recognize each other, and now they're back to normal.
For the third engineering requirement is the drop test. The customer requirement is that the system should be durable and safe. The engineering requirement is that the LED cube can be dropped from at least 100 millimeters, approximately 4 inches, and still work.
Here we're going to do the drop test. So turn that off. We're going to go 100 millimeters, which is about 10 centimeters right there. Drop it. Okay, pick it back up and see if it works. You can see it works.
For the fourth engineering requirement, that is dual algorithms. The customer requirement states that the system should come with algorithms able to display impressive designs. The engineering requirement states that the system is capable of running 2 algorithms at the same time on 2 or more LED cubes from a single computer. In this case, the system is a computer
Here
and
we are
2 LED
testing the dual algorithms. as you can see here, we have the dongle plugged into the computer, and we're going to send 2 different patterns.
Yeah, so it's a little higher.
And stop one of them. The other one's still going. You can see there. Stop the other, start that one. That one's going.
Right now, 800 milliamps.
And now that one's going at the same time.
We made our 5th engineering requirement that our GUI, the graphical user interface or application that you would use, is able to be used on Windows and Ubuntu 12.04. Our 6th requirement is input timing. In this, an LED cube should be ready for the input signal within 10 seconds of being turned on.
In this test, we will be testing the input timing. We have 10 seconds for it to be ready for input. So when I say go, we will turn it on, and hopefully within 10 seconds, it will be ready to go. And go. All right. Obviously, it took near instantly.
Another engineering requirement is the moving algorithms. In this, the system should be able to display an algorithm across 2 or more LED cubes when they're put together.
Here we're showing the moving algorithm. We have placed 2 cubes together, and as you can see, the pattern went from one across to the other and heading back in the other direction again.
Power duration, that's nice and simple. Basically, the batteries on this thing need to be able to run at continuous use for at least 1 hour. If you come during the expo, I bet you will be able to run these on the same batteries. 9th requirement, nice and easy. You just get 10 people. They try to get the GUI we made and start it up and turn one of the LED cubes on in 5 minutes or less, and we were able to get all 10 people to do that. For our last and scariest requirement, we have to make this a little water resistant in case you wanted to take it out on a rainy day and show your friends how cool it was. We're going to spritz it with 100 milliliters of water. That takes quite a while, and at the end it should be able to turn on.
Third is the block diagram. In this, I'll explain generally how each block works in layman's terms. First and foremost is the GUI, or the graphical user interface. This is the application that we use to interface with the LED cubes. And by using this, it will send it will go over USB and tell the USB dongle to tell the cube what pattern to display. So it goes through the GUI, through the USB cable, into the wireless transmitter, which the wireless transmitter then sends radio signals over to the LED cube. The LED cube then reads the wireless transmitter and reads it into the controller. The controller then figures out what you wanted to do. In this instance, we sent it a pattern. So it programs the LED driver here for what pattern to display, and also what level to display. In this, our LED cube will only display one level at any given point in time, but because it's changing so quickly, it looks like that all of them are on at the same time. This means that the controller is constantly switching what level it's displaying and constantly has to reprogram the LED drivers here. Our whole LED cube is powered off of 4 AA batteries. The power from those goes directly into the LEDs, and then also through a voltage regulator, which lowers the voltage for our circuitry, the wireless transmitter, the controller, the LED drivers, and the Hall effect switch, and the level decoder, of course.
future senior design teams. And one really good word of advice is to start early. And it's going to take a lot of time, and you want to start early and work over the break and get a lot of things going right away. That way you'll have a good foundation to work from, and it'll be a smoother transition as you go along with your project.
One other big thing that you should pay attention to is when you buy your microcontroller, it will only have so much flash memory and so much RAM on it. Sometimes you can use more than what you have on your microcontroller and it won't throw an error. But use the command avr-size, S-I-Z-E, in the Linux terminal, if you program in the Linux terminal, and it will tell you how large your program is for data and for RAM and for the flash size, so you don't go over.
My advice is to make a PCB. What is really nice about it is you think this PCB, there are over 100 connections, and making little wires to all that place would be nearly impossible. Now, that being said, there are a few nice things. I would advise going with the SOIC package, which is the larger ones. If you get the ones with the pins on the bottom, you aren't going to be able to test if that pin is working directly, so maybe make a via nearby that you can test. Also, use a flux pen when you're soldering, not only these, but just everything. The flux pen will make soldering much, much easier.